Hello everyone, I'm Furkan. I'm gonna explain our last study on called model-driven engineering for quantum programming, a case study on ground state energy calculations. And what I'm gonna discuss briefly, I will start with the introduction of quantum computing, and then I will give a brief info on model-driven engineering, and then I will define what the ground state problem is, and then I will propose our framework on model-driven engineering for quantum programming, and then I'm gonna deep dive into the platform-independent model for ground state calculations that we create, and then I'm gonna finish with the model-to-model transformation functions. And what is quantum computing? And there's a big shift in computing paradigm nowadays. The classical computers works on bits, which are zero or ones, but the quantum computers uses some phenomenon from quantum mechanics, for example, superposition principle. And quantum computers runs on qubits, which are representing one and zero simultaneously with some probabilities, thanks to the superposition principle. And there's another characteristic of quantum mechanics called entanglement, and if a group of qubits are entangled, it's impossible to describe the quantum state of a qubit independently from the other ones. And this entanglement property allows qubits work together and the process information simultaneously. And using these two characteristics, our computational space grows exponentially larger than storage space. Like for example, if we have 10 qubits, we can represent 2 to the power of 10 bits of information same time. And using those properties, some specific problems can be solved in a much more efficient way on a quantum processor rather than a classical processor. And there are different ways of making this quantum processors happen, and there are different approaches, and in our study we use two of them, so I'm going to briefly explain those two concepts. The first one is IBM's gate-based superconducting processor. In this approach, like the quantum operations are represented as a sequence of quantum gates acts upon the qubits, and this can be a single qubit gate which operates on a single qubit, and it can be also a multiple qubit gate which acts on multiple qubits and make them entanglement particles. And using those sequence of gates, we can represent a complex quantum operation in an easier way rather than a classical computer. And the second one is D-Wave's quantum annihilers, and it originates from the adiabatic theorem, like a physical phenomenon, to solve purely optimization problems. And it basically evolves an initial quantum states towards the minimum energy states, and the minimum energy state represent the problem's optimal solution. Instead of step-by-step operations seen in the gate-based solution, the evolution of a whole system represent the problem solution of the corresponding problem that we mapped into the qubits. But the quantum technologies are on an early age of development, so there are hardware limitations, some quantum noise in the quantum data, and also scalability issues. But besides those hardware related problems, the development tools are so immature. So the modeling languages are not standardized, and there are a lot of diverse hardware systems on different kind of like producers, and we don't have enough support for those diverse systems. And also the models are still under development process, and we don't have enough model verification tools. And also we have some classical models that we are trying to integrate with the quantum counterparts, so we are also lacking some heterogeneity here. So in for those software development sides, we see that model driven engineering can be a good solution for those problems, because it increases the productivity of software development process, while it decreases the complexity of the systems and processes, and it gives some abstraction over the whole process for different platforms, and it automates some even model creation and code generation, and it give a consistency over the whole process, and it also helps for verification, early age verifications on the model generation. And within the model driven engineering, it's important to understand what a domain specific modeling language is. It's a special programming language designed specifically for particularly focusing on the domain idea. Instead of just focusing on finished products on different languages or platforms, a DSML gather information about the domain and creates tools to generate the code for various platforms simultaneously. And it offers tools and concepts that are directly related to the specific field or the domain framework, and it makes the development process even more efficient and better suited than the for the specific domain needs. Let's see how the structure of MDA in quantum programming, and we can see a hierarchy here, and at the base of the hierarchy, the M0 level, or the real concrete object level, represents the real world objects and the systems that exist in the physical world. It can be a QPU or a quantum processor or CPU. And above that, M1 level is the model instance level, creates specific models based on the real world objects, and it can be a classical or a quantum or a hybrid application on those object or above the object level. And on M2 level, meta model level defines the frameworks and the rules for creating those M1 models using DSMLs or GPMLs. And above, the highest level of abstraction is the M3 level, and it defines the languages and the rules for creating those meta models, which is M2 level, and it ensures that the consistency over the whole process. After explaining the vision and giving a brief information on the model driven engineering for quantum programming, we wanted to apply these ideas or paradigms to a real case scenario, and we choose the ground state problem because it has a variety of application on different kind of platforms. And what the ground state problem is, actually, it involves finding the lowest energy state of a quantum system. But this quantum system can be in an application on material science or chemistry or physics. To illustrate, we can give an example about that. For example, we can think of creating a vaccine. Creating a vaccine requires experimenting different combinations of protein lattices for enzymes, for example. And each time we proceed for test or simulation, we need to determine the ground state energy of that corresponding protein lattice. But once our protein lattice grows, the multipartite systems that we are dealing is growing, but the calculation cost grows exponentially higher because of the increased like interactions of the multipartite systems. So as the particle size increases, the complexity of the system grows exponentially. And there are different ways of tackling the ground state problem, and there are some like classical methods to tackle this problem down, and there are even like some approximation methods using artificial neural networks to find the ground state of the systems in an easier way. But additionally, there are some quantum alternatives to calculate the ground state problem. As I explained before, the quantum annealing approach is designed for optimization problems, and we can map this ground state problem into the optimization problem that runs on a quantum annealer processor. And also we can use gate-based solutions for this problem, and it's called variational quantum eigensolver. What does it basically? It's a hybrid algorithm. It's also on the right hand side of the slide. It combines the quantum and classical computation, and the quantum computer part calculates the energy of the state in an easier way with the quantum circuit ansatz on the upper side of the hybrid loop, and then it calculates the energy of the system, and it gives as an input to the classical computer, and it uses some optimizer to optimize its solutions, and it update the parameters on the quantum circuit, and it iterates until it finds the ground state energy of the systems. To represent a multi-party system and solve its ground state, one of the most well-known method is using the Ising model. But to define an Ising model, we need some key information about the system that we want to describe. And like here is on the left side of the slide, those are the required information for an Ising model. We need to know those information to define an Ising model. However, purely knowing this parameter is not enough for ground state calculation. There's a need to develop specific models for each case. And for the quantum computer application, there are two paths, as I mentioned earlier. Like there, each part requires different architectures and platform and some different software development skills, and which are like an adiabatic path and VQA path, as it can be seen in the slide. And our goal is to understand both paths and create a bridge in between them. And first of all, we created a VQA to solve the ground state of an Ising model. And in this slide, there are some examples of three different entanglement type of Ising model with 4 qubits. On the left side, you can see the quantum circuit ansatz for the corresponding Ising model, including circular entanglement ansatz, fully entanglement ansatz, and linearly entanglement ansatz. And on the right side, you can see the iteration of the VQA algorithm as it finds the optimal solution. And in each case, we successfully find out the ground state energies and calculated them correctly. And after implementing the gate-based solution, we also created a model on quantum annealer processor using D-Wave sleep to solve exactly the same Ising models. And for each corresponding Ising model, entangled tight Ising models, the left sides of the graphs shows the corresponding Ising model, and on the right hand side we can see the implemented topologies of those algorithms to the annealer processor inside. Like here are the Ising models, like the quantum system, and here is the qubit that represent that system. And also the quantum annealer optimizes the relationship and finds the ground state energies correctly as well. And after developing exact solutions on different platforms, we proposed a framework, as I mentioned, to solve the ground state problem. And at the real object level, we provided two different APIs that user can interact with. Is one of them is IBM's quantum CPUs and QPUs, and the other one is the D-Waves QPU. And above this, we develop platform-specific models for ground state calculations that connect those M0 level APIs. We created models, runs on those. And one level higher, we have a platform-independent model for a ground state solution, which is built on top of the platform-specific models. And this structure ensures comprehensive and adaptable approach to solve the ground state problem. And let's deep dive into the platform independent model for our ground state calculation. Like what PIM does actually, it automates the ground state calculation by just taking the Ising model parameter as a no-code input. Uh, as I said, we define some parameters that are required to compute the ground state energy in any platform. And with this domain knowledge and PIM, users can calculate their ground state on targeted quantum platforms without developing any models or writing any code on different APIs. In short, PIM simplifies the whole process, and it makes it accessible for user to perform complex calculations across various platforms without needing extensive coding or modeling skills. And besides the PIM, we also created a model to model transformation function. And these functions can transfer the domain information from one platform, one specific, like platform specific model, to another one. Also from a platform specific model to the platform independent model, or vice versa. For example, to explain in a like use case, someone is an expert on quantum annealer, and he has an model and calculations that runs on the quantum annealer, and he want to transfer his solutions to the gate based counterwise. They can use our transfer functions to to translate their domain knowledge to the another platform, and it makes it even faster and more efficient for the users. And what are the practical advantages of PIMs? Before our approach, a user needed to manually design explicit code for platform specific models, such as using like hybrid VQAs in Qiskit, or like the quantum annealer model in D-Wave's Ocean SDK. And they had to perform manual calculation with different cloud QPUs even after creating those models. And it requires extensive platform specific expertise, and the workflow was hands-on, and it is really time consuming. But after implementing these PIMs, users only need to define the key parameters of the Ising model, which is already being required even if they want to run on their platforms. The ground state calculations are automated on the targeted platform, and it eliminates the need for manual coding, and no code development for key parameters make the process even more accessible and user friendly. uh, what do we need to improve in our models, or what is our future work? We plan to enhance our models to do improve their accuracy and efficiency, of course. And then we aim to develop no code interactive interface to make the process even more user friendly. Our goal is extend the scope of these applications beyond the Ising model, or even beyond the ground state calculations. And we will also work on extending the platform support, including more quantum computing platforms. And in conclusion, we demonstrated how model-driven engineering can reduce the complexity in the context of quantum programming. Even though we focused on a small use case, we took a significant step towards a bigger picture. And thank you for listening.